Our next speaker is the head of the Underwater System and Technology Laboratory, Portugal, and is with the EC Department, Porto University. Today, his talk is about the maritime operation with multi-domain robotic vehicle, current trend, and the future development. So I welcome the Professor de Sousa.
Okay, so first of all, good afternoon. I would like to thank you for this kind invitation to participate in this workshop, and special thanks go to Professor Eric Ferron. I haven't seen you in a long time, but I would gladly see you soon, I hope. So today I'll be talking about maritime operations with multi-domain robotic vehicles, current trends and future developments. And what you see here in this slide in the background is some of motivation for our developments. So this white line represents the outer limits of our claim to the extension of the continental shelf. And the challenge is how to achieve a sustained presence in the ocean. First of all, this is the reason why we are here. This is the blue planet, but this is somewhat misleading. Surprisingly, there's not much water in the planet. So this is a sphere representing all of Earth's water. And as you can see, there's not much water in the planet. And this is quite serious because, first of all, there's not much water. And second, because we still don't know much about what is going on in the oceans. So the previous century was called the century of undersampling by Walter Munk. And now let me briefly describe what we do in our lab at Porto University. This is an old picture. Now we have more people, more toys, but we've been designing, building and deploying autonomous underwater, surface and air vehicles for networked operations. Applications include marine sciences, ocean sciences, security and defense. And we've also been developing the software toolchain that enables all of these assets to work together as teams. And this is our vision for a sustained presence in the ocean. There will be multiple assets. There will be lots of different types of interactions, localization links, communication links, interoperated radio and underwater, sensing links, for example, when you talk about the acoustic tomography, mixed initiative interactions, meaning operators in the planning and control loops. Vehicles will come and go, same thing with the operators. There's also the issue of scalability. Right now, we know how to operate, let's say, 10, 15 vehicles at a time. What about 100? What about 1,000? We've also been using vehicles as data mules. There's also the issue of distributed computations. And we've also been using vehicles to basically, or for launch and recovery of other vehicles. But in our vision, we want to treat all of these vehicles and systems as a system that has properties that are a function of the vehicles, of the communication networks, and of the interactions that establish over these. So we want the system to have organization-like properties. But this is not PowerPoint engineering. So we've been developing the tools and technologies to achieve this goal. So assets, we have lots of different assets. Most of them were designed and built at Porto University. We also bought a few other ones, such as the Autonomy, like our friends from NTNU. We also have some very exotic vehicles. I don't know if you can see my pointer, but this is an octocopter that can take off and land from water. Most of these vehicles, if not all of them, share the same computational hardware and they use the same software, and they are interoperable, meaning that they can talk to each other. So this is our workhorse, the LAUV, two different versions, upper water column, endurance 50 hour plus, and mapping. There's support for multi-vehicle operations, and you have over 80 LAUVs in action worldwide. This is because of our spin-off, Ocean Scan. The operation is quite simple. You just need to make sure that there's water when you throw the vehicle into the water. And another very important component of what we do is our LSTS open source software toolchain. We have Dune that runs on board the vehicles, IMC, which is our protocol for communications. All systems in our network stock IMC. Then we have Neptus, which runs on your computer and is the way for you to interact with the system. And then you have Ripples, in which you can do exactly the same thing over the web. And with these, we can have a software-enabled networks vehicle system composed of different assets, such as the ones that you see here. There's a spin-off, as I told you, OceanScan. They've been selling mainly to Europe and to Asia, lots of different customers, including several navies. And this picture is quite relevant. This is an LUV, front page of Science Robotics, and this was an article put together by our friends from NTNU. I would also like to briefly allude to this project, this H2020 project. We have several other projects, but this one is very special for one reason. This is an infrastructure project, H2020, 15 partners, and most of the key players in marine robotics in Europe. And what is the project about? So 3 main things. The first one is to provide access for free to our infrastructures. And you see some of these here. So people can submit or could submit proposals to use these infrastructures. And then there was an international panel for evaluation. And we had over 50 transnational access projects approved and implemented. We also worked on making systems more operable, high specialized training, large-scale experiments, worldwide cooperation, and interactions with other research infrastructures. Just to give you a sense for the footprint in terms of TNA access, transnational access, in blue you see locations of the partners, and in yellow, green, and red you see locations of institutions that successfully apply to use our infrastructures and successfully demonstrated their projects. So a very interesting footprint. Now switching gears and going into operations, we've been operating in lots of different places. We've been organizing large-scale exercises. We have deployments from shore, from ships, and also from manned submarines. This is quite unique. Typically, we have over 100 days of operations per year. And I don't have updated figures here, but from 2018, we had over 4,000 kilometers underwater and over 200 flights for our UAVs. One example, simple but quite relevant, mapping the plume of the Douro River. So the river goes into the ocean. There's fresh water meeting kind of ocean water. You can spot the plume from the air, but we've also had vehicles that kind of mapping the plume as it moved. And what you see here is a representation of one of those missions. So if you can track my pointer, this is basically the plume. And then the AUV was a kind of performing these transects zigzagging along the plume. If you look at transect 1 here, you can see the salinity plot. So you can see fresh water at the surface, and then again, salty water here. So, and by doing this, you have a very interesting characterization of the plume. And this is very interesting for marine sciences, for biology. And actually, there's also a mechanism for the generation of internal waves here. Something completely different that we did in the Azores in 2015, during the REP exercise, done in cooperation with the Portuguese Navy, also our friends from NTNU and NASA AIMS. So we had multiple assets deployed offshore from this vessel from the Portuguese Navy. And the idea was to track whales that had been tagged And at the same time, while we were doing that, measuring environmental parameters close to the whales. So this was done with the help of two planners, one on board that would task multiple assets, and then another plan on board each vehicle that would take care of execution for each vehicle. Without going into details, it's fast forward from a kind of a real operation. So what you see here is a UAV flying and trying to find the whale. And at the same time, we had AUVs in the water measuring environmental parameters close to the whale. Another example, a bit more complex, this took place in the RAP exercise in 2019 in Portugal. So we had the WAMV, the surface vessel, from the University of Hawaii. We also had a seabed node from the University of Hawaii. And then we had AUVs from the Naval Undersea Warfare Center. These are kind of gray ones here. And AUVs from Porto University, the LAUV. And then we also had this exotic flying modem that I alluded to before, which is an octocopter that can take off and land from water. And this is how things work. So the operator would send mission commands to the WAMV that had a communications gateway that would forward these mission commands to the AUVs, or the operator could send mission commands and mission plans to the flying modem when this was within the line of sight. Then the flying modem would land close to the seabed node and then would send messages to the seabed node with mission plans, commands, and then AUVs would go by the seabed node to basically extract these mission plans for execution. Something else that we did, and again, these are just a few examples, optimal estuary ingress under tidal forcing. So there's this estuary, very strong currents there. And then we had a high-res model of the currents with approximately 5 million points spreading space and time. And the question was where and when to deploy an LUV to reach the target represented here by this dot, in minimal time while staying clear of obstacles. So we had a very elaborate approach based on dynamic programming on kind of a numerical method to solve very efficient to solve the Hamilton-Jacobi-Bellman equation. And what you see here is one example of an experiment, length 13 kilometers, 3 hours. Velocity gain because of the currents was 28%, and the difference between what the vehicle did and the estimated time of arrival was 2 minutes. There's much more to it, but I'm not able to, let's say, talk about it for the obvious reasons. Something else that was also demonstrated in the RAP exercise 2018, so we had AUVs and ASVs, we had one operator, and we had system level planning and execution control, for example, for coordinated mapping. Here's an example. First of all, these guys were performing some formation control. And then we'll switch to a different problem, which is a kind of a cooperative mapping, coordinated, in which AUVs were tasked basically to map different areas, and then we induce some faults, and those guys would retask using ACOMs without any human intervention. Another different achievement was in 2018, we went to the Pacific. This was funded by the Schmidt Ocean Institute. So 3 weeks on board the RV Falcor. And our team, so we had people from, then again, our friends from NTNU, from the universities of Rhode Island, University of Harvard, and we also had collaborators from NASA Ames, from the Portuguese Navy and SINTAF. And basically, we went after the Northern Pacific subtropical front to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal resolution. So here's the video. I hope you can hear the sound. This was approximately 1,000 nautical miles west of San Diego.
During this expedition, our team has created a system to conduct oceanographic surveys with unprecedented levels of detail and scale. Approximately 1,000 miles off the coast of Southern California, we are studying the subtropical front. Here, two masses of water collide, which generate a unique mix of physical, chemical, and biological features. Before the expedition, autonomous vessels helped us determine the approximate location of the front. When we arrived here, we deployed CTDs to gain a more precise understanding of its spatial dynamics. Our autonomous underwater vehicles, which were specifically designed for this expedition, can cover hundreds of kilometers and stay in the water for up to 50 hours. They travel in a yo-yo pattern, sending real-time data back to the ship every time they surface. Our fixed-wing vertical takeoff UAVs can fly faster and further than quadcopters and carry a variety of sensors. The data our autonomous vehicles collect helps us locate biological hotspots where we conduct more detailed sampling.
We are deploying very advanced technology that needs to be refined through experimentation, and by doing that we hope to establish some of the foundations for the future of oceanographic surveys.
So this was a system architecture. So we deployed from the Falcor. We had some very nice SATCOMs. We interacted with all of the assets using SATCOMs. And then we had the Ripples, a cloud-based system to support all of our operations. So we had a control center in Porto and another one on board the Falcor. We operated in non-stop 4 shifts per day. And this is a kind of a picture of the mission control center in Porto and mission control center on board the Falcor. Just to give you a sense for some of the things that we did. So in the background, you see a sea surface temperature map. So red means kind of higher temperatures, and blue means kind of lower temperatures. And then superimposed on these, you have tracks of the AUVs color-coded by salinity. And there's a very interesting correlation between these tracks. Keep in mind, there's also a time shift, because this mesoscale mapping took approximately 1 week, 50 nautical miles by 40 nautical miles, but still very interesting. We learned a lot. We had our AUVs performing automated front detection and tracking. We also performed high-resolution coordinated sampling, in which the AUVs, the Falcor, and UAVs would move information to provide a synoptic view of the ocean in that area.
So we take all these different systems that go beyond the footprint of what a ship can do. They could be 20 miles this way, 20 miles that way, and help us understand the oceans a lot better than we do now.
So basically, we were extending the footprint of what a ship can do. Then again, one note from Eric Schmid: technology first, new technology should drive the SOI science program. Accomplishments: so we successfully demonstrated a novel approach to observe the ocean with persistent network vehicle systems. Operations: we operated for a long time, and systems and technologies demonstrated in these crews are also applicable in other areas of the world ocean. Now, finally, let me briefly discuss future developments from vehicles to systems. One quote from Praveen Varaya and other colleagues, this is from '78, and they said that they don't believe that existing mathematical tools are powerful enough to define a preferable structure for decentralized and/or hierarchical control. And the fact is, this is still a challenge. What are we talking about? So if we look at all of these different missions and operations, and we can try to come up with a sort of the taxonomy, this is not very formal, just a kind of as a way of discussing. So we could think about classification in terms of number of assets, vehicle and functional heterogeneity, deliberative planning on board, off board, dynamic teaming, mission complexity, built-in resilience, cloud-based interactions, communications, cost of losing an asset, logistic support, interoperability, and persistence. And you see that some of these cases, so I talked about the SOI cruise, talked about the kind of mapping, so fare differently here, but we still are facing lots of interesting challenges ahead. And another important observation is that we are not talking about swarms, far from that. We need some notion of hierarchy. We can discuss this later on. Another important observation is the notion of dynamic reconfiguration, which is a common feature of communicating systems. The notions of link, not as a fixed part of the system, but as a data that we can manipulate, it's essential for understanding such systems. And so we need to evolve to notions like value, evaluation, and function. We need to evolve from these notions into those of link, interaction, and process. This is a quote from Robin Milner, Turing Award in '91. And another important thing is the notion of mobility, which is quite common in the software community. I won't go into control mobility, data mobility, link mobility, object mobility, but one observation about mobile computation, when you have mobile software that can go from one network node into another network mode, and also mobile computing, in which you have mobile hardware that can serve the computational needs in a given location. And then we also need different models. There were several attempts in the computer science community, one from Robin Milner, which was the idea of bigraphs, which is based on a graphical model of mobile computation that emphasizes locality and connectivity. This is very important, because keep in mind that you can have mobile software, but you can also have mobile hardware. And in this framework, you had a place graph that had a structure of a tree, and a link graph, a hypergraph, that basically established relations. And when you put two together, this would describe the state of the system. And then the system would evolve through different bigraphs. And then there were bigraphical reaction rules explaining how the system would evolve. Still, this proved to be very complex and at the same time, very limiting. And just for the sake of reasoning, or for brainstorming, if you will, think about something similar. Think that we have this system, vehicle A, that moves in X and Y. This vehicle has sensors, communications, the motion controllers, actuators, and physical entities like sensors, and also has a computational environment in which you can have several processes, or if you want, algorithms, or there could be other vehicles, exactly the same thing. Those could be in communication range. If they are in communication range, then you can communicate over these. And then if you look at this, and if you look at these systems in terms of models, you can get inspiration from the actors model, which was introduced by Carl Hewitt, then again, a long time ago. But the interesting thing is that if these guys are communicating, then you have physical entities that are vehicles with unique names. These can be composed and can enable mobile locality. And then we also can have transition functions that depend on physical interactions with other physical devices in the environment, and you can decouple the sender from communication. So this is basically describing what you're seeing here. But then you can go one step further, right? Because since you have communications, then you can move processes or software, if you will, from one vehicle to another vehicle. Then you can compose processes or algorithms, if you will, based on different vehicles, since you have communications. And then you can even go one step further, which is block communications with other assets and form a team. And the team can also have a unique name, can also have a unique command set, and there could be more to it. And then you can think about, okay, how am I going to go about specifications for the behavior of these systems? So think about, let's say, time interval, and you can say that in this time interval, team X will be located in a given region and vehicle C will be located in a different region. Then in the next time step, these guys can move to a region phi and then start interacting. And this will be a sort of a specification for this type of system. Then what will be a run of a system? Imagine that you have time, you have space, you have a bunch of vehicles in this region here, another bunch of vehicles in this region here, and then they can move to other regions. They can then connect, establish teams. Then some vehicles can leave these teams, go to other teams, and then eventually go back to base. So what are the new challenges? And I'm almost there. So given a specification for the behavior of a set of vehicles, synthesize a set of computational entities to be composed in the computer sense with the vehicles to satisfy the specification. So we need a notion of behavior equivalence. And what will be a run of the system? It will be a coordinated, sequential, and parallel execution of classical control problems formulated in extended control spaces. And then you need properties such as continuation, information reachability. So you want to make sure that information reaches vehicles when it's needed, termination, well-formedness, and encapsulation. And some final thoughts. It's tough to make predictions, especially about the future, but in terms of trends, the pace of change is accelerating. No robot is an island, and we need new models of cooperation and networking. And we need to think about the power of networking. We need to think practical, think big, and think sustainable. So thanks very much.